Hey guys, good afternoon. Graham Reese going live here, doing some biochem full content review into UWorld questions. I'm just doing this for myself, keeping myself accountable. I know nobody's gonna be here, but you know, gotta lock in. Okay. Share screen.
Chemistry. So we're done with organic one. Hello, everyone. Welcome back. Today is going to be our first day covering biochemistry. So we're done with organic chemistry. We're moving on to biochemistry. For everyone watching back home, thank you for sticking around. Check below in the description for the links to all of our recorded lectures, including our sign-up sheet for our email list and all of my study guides and notes that I upload to the drive. Okay, so for everyone who's here today and everyone back home, this is biochemistry. This will most likely be the bulk of the program because I think that biochemistry, in terms of the science section, this is the bread and butter of the MCAT. This is kind of what you have to get through. This is where you have to kind of put your head down and just deal with it. There are certain chapters in biochemistry that are excruciatingly long that require a very, very in-depth understanding of biological and biochemical processes. Endocrinology comes back up, periodicity comes back up, organic processes come back up, nomenclature is a big thing, et cetera, et cetera, et cetera. So today, for our first day, we will try to get through the first two chapters. We might not even be able to do that. I may need to extend into next time, but this is going to be chapter 1, amino acids and proteins. But the proper name of the chapter in the book is amino acids, peptides, and proteins. So what better place to start than to define those three terms? So who here knows what an amino acid is?
Amino acid is a compound that can make a peptide bond or an amide bond.
Mm-hmm.
It has an amino group on it, an R group.
Yep.
It can be aromatic, nonpolar, acidic, and an SH bond of serine.
That's fantastic. So that's a very holistic definition. So let's boil that down to a general term to cover all amino acids. So basically, it is a carboxylic acid with an amino group on it or an amine group on it. It's a carboxylic acid. So let's boil that.
Bro. Huh.
So let's boil that.
Figuring this shit out.
So let's boil that.
Figuring this shit out.
With an amine group on it. It's an amino acid, right? Now, when we think about amino acids, we think about stuff like this. And you may realize that I'm writing them with charges. And the reason I'm doing that is because in biochem, unlike in orgo, we show all of our molecules the way they would be presented at physiologic pH, right? So, like I said before, and think back, this is once it already starts. It begins coming back right now. Think back to the way. So that's a very holistic definition. So let's boil that down to a general term to cover all amino acids. So basically, it is a carboxylic acid. Let's boil that down to cover all amino acids. So basically, it is a carboxylic acid. Let's boil that down to cover all amino acids. So basically, it is a carboxylic acid with an amino group on it or an amine group on it. It's a carboxylic acid with an amine group on it. It's an amino acid, right? Now, when we think about amino acids, we think about stuff like this. And you may realize that I'm writing them with charges. And the reason I'm doing that is because in biochem, unlike in orgo, we show all of our molecules the way they would be presented at physiologic pH, right? So like I said before, and think back, this is once it already starts. It begins coming back right now. Think back to the pKa table I gave you. So what was the pKa of ROOH, right? Like a carboxylic acid, that would be anywhere between 4 and 5, right? And then the pH of NH4 plus is going to be 9.4, right? And if you remember, in order to figure out either the protonation or deprotonation of weak acids and weak bases, right, we need to use the Henderson-Hasselbalch equation, which is very, very important in biochemistry. pH equals pKa. Who can finish the Henderson-Hasselbalch equation? What is it, plus or minus log? Is it plus or minus? This is the thing everyone forgets. Huh? Who knows the Henderson-Hasselbalch equation? I believe it's plus log A minus over HA. But I'm going to double check that just because it's something I also mess up all the time. It can have two forms. Yeah, so it's plus log A minus over HA. You could also do minus log inverse, right? Because that's how logs work, correct? How are you guys? You doing all right? Welcome back. I said that I would start this this session with a story. So let's finish our definition, and then I'll tell the story to all you guys since a couple people just filtered in. Because I wanted to share my story with a bigger crowd. It's funny. So these are amino acids, and we were talking about how at physiologic pH, we want to know how these groups are protonated or deprotonated. So we know the physiologic pH is what? If I say the pH of the body, what do you immediately say? Off the top of your head. Around 7, right? But our blood is slightly alkaline, the tiniest bit. It's 7.4. Keep that in mind. 7.35 to 7.45. 7.4, right? And any deviation from that is pretty bad. So going to 7.5, bad. Going to 7.3, bad, right? 7.4, we want it right there. And that becomes very important, especially in medical school when you start talking about acidosis, alkalosis, et cetera, et cetera. And we'll talk a little bit about why pH is such a big thing, especially when we talk about amino acids, proteins, et cetera, right? Okay. So an amino acid is a carboxylic acid with an amine group on it, right? So here's our carboxylic acid, right? And this amino acid is specifically called an alpha amino acid. Why is it called an alpha amino acid? Well, obviously a carboxylic acid has higher priority than an amine group, right? So this is the carboxylic acid carbon, and this is the alpha carbon, and on the alpha carbon is a amine group, alpha amino acid, right? That's how the nomenclature comes around. Amine group. This is the carboxylic acid carbon, and this is the alpha carbon, and on the alpha carbon is a amine group, alpha amino acid, right? That's how the nomenclature comes. Is a amine group, alpha amino acid, right? That's how the nomenclature comes around. Now, why did I bring up the pH? The carboxyl group, or what we call the carboxyl terminal when it's a peptide or a protein, has a pKa around 4 to 5, right? Which means that at a pH of 7.4, which is more alkaline than the pKa, it's mostly or entirely deprotonated. And for the amine group, the NH4, right, which has a pKa of 9.4, because you always consider them in their protonated form when you talk about pKa, right? 9.4, 7.4 is 2 pH points, or 2 like acidity points, whatever, below, right? Which means this is a lot more acidic than this, which means this is entirely or mostly protonated, correct? Okay. And that's going to come in handy when we start to talk about R groups. Because most of the time when we're talking about amino acids, we're talking about ones with groups on them, right? And that R group for amino acids in our body, it comes out. If you write the NH3 to the left and the carboxyl terminal to the right, the R group comes out of the board on a wedge, right? And that is a, what, L or D amino acid. In our body, it's D sugars and L amino acids. So this is an L alpha amino acid. So what's a beta amino acid, right? Not that you need to know it, but just to make the differentiation, right? Exactly, so you got an alpha carbon, a beta carbon, and then you got NH3. Okay, so that is amino acids, right? And then we said that these have the capacity to make amide bonds, right? Or peptide bonds, and they also have R groups that can interact with the environment in special ways, depending on the identity of the R group and its chemical properties, right? Cool. And its physical properties as well. We'll take a look at that. The physical properties of the atoms and like the space they take up. So we'll see how that kind of affects protein structure and peptide structure down the line. Let me tell my story. All right, so 3 days ago, I was home with my mom because I had Monday off after I finished my round of exams. So they gave us off from Friday, Saturday, Sunday, Monday, because Friday was Veterans Day. Saturday, Sunday is the weekend, and they didn't give us off on Monday. I just had lecture, but my lectures aren't mandatory, so I decided not to go to school that day. Okay. So I'm home on Monday, and my mom just recently had surgery on her arm. I think I told you guys that, right? So she had surgery, and she's like getting better. She's doing pretty well. She's going to PT. She's getting better, everything like that. But one thing she can't do yet is go grocery shopping. She can't pick things up with the right hand, heavy things. So what she does is she like orders pickup to the grocery store, and she can drive. So she drives herself there, and then just goes to pick it up whenever it's done. So she can't. So that's how she's been doing it. But since I was home, she's like, "Hey, can you go pick up the groceries?" I was like, "All right, totally, 100%. I love doing things for my mom when I'm home." So I take her car. There's a lot of groceries, and her car's bigger than mine, right? And I'm about to go, and she's like, "Wait, you might need my ID because it's under my name." I was like, "Okay, sure." So I take her ID and I go to the store. They don't ask for her ID, right? I pick up her groceries, I come back home, I drop it off, and then I come back to Brooklyn, right? Okay, I'm in Brooklyn, Monday night, Tuesday, Wednesday, and Thursday. I'm back home this morning. So I came in from Long Island today, right? So I'm home this morning, and I'm in the shower, right? And I get a call from my mom. No matter what I'm doing, right? No matter what I'm doing in life, I'll pick up a call from my mother, even if I'm in the shower. So I step away from the water in the shower, and I pick up the phone call from my mom. I was like, "All right, Mom, what's up?" And she's like, "Do you have my driver's license?" And I was like, "No, why would I have?" And then like while I'm saying that, I have a flashback to 3 days ago when I picked up her driver's license, put it in my wallet. I was like, "Fuck." Okay, I was like, "Okay, let me check." So I step out of the shower, I dry myself off, I go get my wallet, and first thing in my wallet is my mom's driver's license. I was like, "God damn." So I take a photo of her driver's license. I send it. I don't know why she needs. She didn't get pulled over, and she's at work, right? So I send a picture of her driver's license, right? And then she calls me back like 2 minutes later, and she's like, "So you mean to tell me that you can memorize all these facts, and you can teach all these kids, and you know all this information, and you got into medical school, and you're this smart, and you forget to put my driver's license back in my wallet when you come home?" And I just wanted to share that story with you guys, because last time we were talking about how I am not a smart person, right? So as good as I am at this stuff, I promise you that outside of these walls, I am the most forgetful and absent-minded person you'll ever meet. So that's a story about me outside of the education setting. Here's hoping, right? I'm a very, very forgetful person. It's gotten me into a lot of trouble with my family. Not like bad trouble, but my mom's like, "I told you to do this like 4 times." And I was like, "Yeah, I forgot all 4 times." I like to think I'm a good kid. I like to think. So, amino acids, right? What are peptides then? Peptides are basically just amino acids strung together, right? It's normally like a short quote unquote chain of amino acids, right? And how do they come together? Well, they come together like this. So we have an amino acid here, we have an amino acid here, and it adds onto, and those two come together, right? And if you can imagine, what's kind of going to happen is that you're going to subtract a water molecule from here. So you're going to grab 2 of those H's from there and that O over there, right? And it's going to form something like this. O, N, H, and carboxy terminal there. And this is called a dipeptide, right? And the way you know you linked your amino acids together correctly, one of the carbonyls will face down, and the next one will face up, and the next one will face down, and the next one will face up, right? Cool. Remember, what did I say was special about this bond right here? The nitrogen does what? The electrons of the nitrogen, they do what? They resonate, right? Because that's an sp2 carbon right there. So that resonates like that and like that. So if you wanted to, you could take a dipeptide, right? You could take a dipeptide. Right, because that's an sp2 carbon right there. So that resonates like that and like that. So if you wanted to, you could take a dipeptide, right? You could take a dipeptide, hello. And you could show that resonance occurring across the amide bond, or what we call the peptide bond, right? Because when we're talking about amino acids linked together, it's no longer just an amide bond, it's a peptide bond. So that's H3N, O minus, double bond NH, positive charge, carboxy terminal. Right. So now we realize something very special, that the nitrogen, even though it looks like it's sp3 inside of the neutral form of the peptide, when it resonates, it reveals that it's actually sp2. And that tells us that the nitrogen position, along with the carbon position of the peptide bond, it is what? What's the electron geometry there? Or sorry, what's the structural geometry there? What's the shape? What's the shape along that axis? It's trigonal planar. Like we talked about last time. The sp2 structures, they are trigonal planar. And that indicates, and this is a very specific word, planarity. It indicates planarity against what order, against what sort of domain of the molecule? Here. This entire domain right here, is planar. It's flat. You get questions about that on the MCAT all the time. The planarity of the peptide bond, right? The quote unquote planarity of the peptide bond. Planarity of the peptide bond, right? The quote unquote planarity of the peptide bond. Right? So it's flat, it's planar. What do we mean by planarity? So imagine you're back in math class, right? And you're thinking about an XY coordinate. That is a plane, in that plane, right? And then you got to calculus and they throw a Z-axis in there. And now it's a 3D thing, but it's no longer a plane. A plane is a flat structure. So if I wanted to, I could take the nitrogen bound to the oxygen like this. And if I drew it like that, this would be structurally correct, right? That it's flat against this plane. But one thing to remember is that the p orbitals that exist on the nitrogen, the carbon, and the oxygen are in the perpendicular plane to the orientation of the molecule. So if the molecule is flat in the plane of the board, the p orbitals will be coming out at you and back into the board, right? Always remember that the planarity of the molecule in an sp2 species, the p orbitals go in the opposite direction. They go perpendicular. They make 90-degree angles against that plane. Does everyone understand what I mean by that? Right. Molecule in sp2 species back into the board. Right? Always remember that the planarity of the molecule in an sp2 species, the p orbitals go in the opposite direction. They go remember that the planarity of the molecule in an sp2 species. The p orbitals go in the opposite direction. They go perpendicular. They make 90-degree angles against that plane. Does everyone understand what I mean by that? Right. The best way to describe this is by drawing a carbocation. If I were to draw a carbocation within a specific plane, and I'm going to show you in the opposite plane to the board, right? So if a carbocation, which is an sp2 structure, everyone would agree on that, exists like this, and imagine that this is our carbon, because a point takes up no space, correct? So it's taking up no space in the plane of the board. You can imagine that there is 1, 2, 3. And that's all out of the plane of the board. One of them is going in an infinitesimally thin line along the board. One of them goes back and one of them comes out, right? So none of this is in the plane of the board, but that means the p orbital will be going straight up and down in the plane of the board, perpendicular to all 3 of those other orbitals. Does that make sense? You have to imagine that every single sp2 structure with p orbitals going through it is like that, right? Okay. So the planarity of the peptide bond, that's what we're getting at here, right? So that's how you make peptide bonds. So what's a protein? It's a much longer thing. These are sometimes called polypeptides. And normally, they're called proteins when they're functional. Huh? Oligopeptides, dipeptides, tripeptides, they may have some function, but proteins have special functions, right? And they're much longer chains. I don't specifically know the textbook definition of a protein off the top of my head, but normally when we talk about proteins, myoglobin, hemoglobin, keratin, these proteins have specific functions, and they are long, long, long chains of amino acids, right? Very long chains of amino acids. We'll get to that. We'll get to that. Any questions about what I put on the board?
I have a question. What about the states of the amino acids? We need to know the states if they have both positive and negative terms.
We'll get there. We'll get there. We'll get there.
As a amino acid chain as well, is every part that exhibits the.
Let me erase. Everyone good with this? Okay. So that's a really, really good point. And that actually gets into the way that amino acids kind of bond to one another. So the question there, if the microphone didn't pick it up, was that if we were to bond amino acids together in a long chain, right, would every single peptide bond form a planar structure? Is that what you're saying? Yes, because by definition, a bond between two amino acids is a peptide bond, which is an amide bond, which means that the nitrogen is resonating its electrons to the carbonyl position, right? And that necessitates that it's planar. There's 2, there's 3, and there's 4, right? And how do you know it's 4? You count the R groups. That nitrogen's going to resonate there, that one's going to resonate there, that one's going to resonate there, and then, right? And since all the nitrogens are resonating, it is planar along this domain. Because by definition, right? And since all nitrogens are resonating, it is planar along this domain. And along this domain, and then along this domain, and then along, well, obviously this domain, right? Because that's a carboxylate group. Yeah, what's up?
R groups can not be planar too, right? Like isoleucine.
We will get to that. We will get there. We don't know what R groups are yet. Okay. So now that we've talked a little bit about amino acids and peptides and proteins in general, let's begin our discussion about the structure of amino acids. And there's 20 of them that you need to know, right? There's 20 amino acids that you need to know about, right? So first, you have your non-polar, non-aromatic side chains. All right. You guys ready? So the first class is non-polar, non-aromatic. These are also known as aliphatic amino acids. And there are 7 of them. One, 2, 3, 4, 5, 6. We're going to leave the last one blank. There's something special about the last one. Okay. So the first one is actually done for you because the R group is a hydrogen, right? The R group is a hydrogen. Who knows the name of that amino acid? It starts with a G. Glycine. This is glycine. And next to it, I'm going to write 2 things. And every single time I wrote down an amino acid, I wrote down these 2 things next to it to ingrain them in my head. A 3-letter code and a 1-letter code. The 3-letter code for glycine is GLY, and the 1-letter code is G. So that is the 3 ways that you can write glycine, the 4 ways. One of them is symbolic, one of them is a word, one of them is a shortened version of the word, and one of them is a letter. The letter does not always correspond to the first letter of the amino acid. Sometimes people got to double up. Like threonine and tyrosine fucking hate one another because both of them begin with a T. So one of them has got to be T and one of them's got to be Y. I just gave it away. The tyrosine is Y because threonine already had T. So you go to the second letter of tyrosine, it's Y. Some of them make absolutely no sense. Like lysine being K. What the fuck? Or glutamine being Q.
Yeah, so why do you do both?
Because they get referred to in passages. Sometimes they'll just say, oh, amino acid G, and you gotta know it. Or they'll say, hey, here's an amino acid chain. Tell me the pH of the charge of this chain at normal pH. You know what they're going to give you? They're not going to tell you glycine, leucine, isoleucine. They're going to show you this, and you got to translate that. Non-aromatic.
Hello? Hello. I'm good, how are you? Yeah. Good. I done some biochem. Yeah. Yeah, it was good. Thank you. No. I did half this morning and half this evening. No. Yeah. I don't know, let's see. Yeah. Yeah. Okay. Okay, bye. No, I didn't. You can just get Q-tips. There's no pain or any discomfort. It just kind of irritates it now. Okay, bye. Thank you very much.
Because they get referred to. Sometimes they'll just say, oh, amino acid G, and you got to know it. Or they'll say, hey, here's an amino acid chain. Tell me the pH of the charge of this chain at normal pH. You know what they're going to give you? They're not going to tell you glycine, leucine, isoleucine. They're going to show you this, and you got to translate that. That is a really common question on the MCAT, which is why every single time I encountered any amino acid, I put that down. You are. Not pencil and paper. So you're given a notepad with a erasable marker, or I think it's an erasable. Or is it something? Yeah, it's like some sort of marker. and you're given a pad. And then if you want to swap out the pad, you just raise your hand and they swap out the pad for you. I'll tell you some funny stories about when I took my MCAT. I had really long hair when I took my MCAT. So my hair was like down to here. I'll show you guys a photo whenever we're done. And when I got in, I like scanned my palm, because you have to scan your palm in order to take the MCAT. They like scan your palm veins, like one of the ways to distinguish people other than a retinal scan and a palm scan, right? They scan the veins in your hand. So I scanned my palm. I was about to go and they're like, hold on, shake out your hair. And I was like, what the fuck could be in my hair, dog? So I like shake out my hair for them. There's something there. Like, all right, go take your exam. And then at one point, I was like fiddling with my hair during the test. And one of the proctors came. And this is a 7.5-hour exam, right? So I'm like fiddling with my hair during the test, like while I'm reading. And they're just like, can you stop touching your hair? I was like, shut the fuck up, bro. Like, what are you on about? It's so annoying. All right, anyways. What's next? So that's glycine. Next we got, what color do you guys want for the R groups? Red, blue, red? All right, let's do red. Next we got just a methyl group. That's going to be what? No.
Go down.
Nope. Alanine. A-L-A-A. A-L-A-A. There's another amino acid that is a derivative of alanine. What's it called? Phenylalanine. Phenylalanine, right? What does phenyl mean? A benzene ring, right? Because phenol and phenyl don't mean the same thing for some reason, right? It's called phenol because it's an alcohol that has a phenyl group on it, right? So it's a benzyl alcohol, right? Okay. But for some reason, a benzyl group is not a benzene ring. I think a benzyl group is like a benzene ring with a methyl group on it or something like that, right? It's really dumb. That's alanine. What's next? Not phenylalanine. Because phenylalanine has a benzene ring on it, which makes it aromatic. So it's part of the aromatic amino acids, right? Next is valine. And that one's easy because it's a V. You take the amino acid and you attach a V to it. That's valine. 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 V-A-L-V. And if you look at the one-letter code, it tells you the R group. Next is, anyone know? Well, you wouldn't know, it's like in my notes. So next is leucine. Basically, valine's older brother. Or sister. Right? Leucine, L-E-U-C-I-N-E. L-E-U-L. How many carbons does it have? 1, 2, 3, 4, right? And if it has 4 carbons, we can isomerize that. And if we isomerize leucine, it's called isoleucine, the isomer of leucine. It looks like that, isoleucine. So it's leucine, but isomerized. And unfortunately, the 3-letter code isn't iso. So isoleucine, it's I-L-E, I-L-E, isoleucine. Next, this one has a sulfur in it, but it's not cysteine. What is it? Methionine. Very good, methionine. Hold on. Oh yeah, I left it blank, never mind. Okay, methionine. The 1, 2, and we got a sulfur and a methyl group. What's the geometry about the sulfur? We've got tetrahedral electron geometry with 2 lone pairs. sp3, yes, but the geometry, the molecular geometry. If there's 2 things attached, it's bent, like we talked about last time. Whenever 2 things are attached, it's bent. This is methionine. What's the 3-letter code for methionine? Met. Met M. You will oftentimes hear bacteria starting their proteins with N-formal methionine, right? And our start codon also codes for methionine. I believe methionine starts most of our proteins. Like that's where translation starts. What's the difference between transcription and translation again? Transcription first. So transcription is DNA to RNA, and then translation is RNA to proteins. So imagine that proteins are the language that everyone can speak, right? So you translate into the language that everyone can speak. You translate into protein. mRNA to protein is translation. Transcription is transcribing a template. The template is the DNA. You transcribe it to mRNA, right? And you tweak it, you make some modifications. What are the 2 big modifications that we know about on mRNA? Modification and a 3 tweak it, you make some modifications. what are the two big modifications that we know about RNA? There's a 5' modification and a 3' modification. There's a poly A tail and a GTP cap. I forgot which one's on which one. I believe it's I think, well, it depends, like 5' or 3', because they're both the end. I think it's a 3' poly A tail, right? I'm not 100% sure. Someone look that up, but we'll talk about it later. All right, the last one is a little fucky, right? The last one's a little fucky. Instead of 3 protons, write down 2, right? Not because the pH has changed, or it's different, or the rules of chemistry have broken, but because this amino acid loops in on itself. 1, 2, 3, 4, 5-membered ring. Makes a 5-membered ring, and that makes the nitrogen positive again. This is what? Proline. Proline. And the one thing I want you to know about proline, does anyone know the joke? Pro, P, right? Proline is really kinky, right? Proline is really kinky. And in about 30 or so minutes, when we're done with the amino acids, we'll talk about why proline's kinky. Does anyone know why proline's kinky before I explain it later? I want you guys to think. Yeah, what's up? Right. So this bond is pretty stable, right? Because it's a carbon and nitrogen bond, and you're not gonna lose that, right? When you form an amide bond, but this can still form an amide bond if we lose one of those hydrogens and then give it back its electrons. It can participate in bonding. So when the amide bond forms here, right, it's gonna be strange. It's gonna form in a strange way. So we'll realize that when we're trying to make chains, proline will come in and it'll fuck up our chain a little bit, right? And what happens is we get a kink in the chain, right? So we'll have chain, turn, chain, turn, whenever the proline comes around. And those are called kinks, right? Have you guys ever helped out your dad or your mom around the garden? They said get the kink out of the hose, right? The hose is like kind of, bent like that, and you gotta unkink it, right? So proline induces kinks inside of straight chains of amino acids. So it's kinky, right? Just walked in. If you want to take a photo of the board, please do, because we're going to move on. Okay, cool. You too good for it? Right, so am I. All right, so those are our 7 aliphatic amino acids. And off the top, we've got class 1, glycine, alanine, valine, leucine, isoleucine, methionine, and proline. GAV-LYMP. Lymphage, yeah, lymphage as well. That's bad. Huh? It's like my mnemonic for the citric acid cycle. Can I keep selling sex for money, officer? Or you could be a fucking crackhead like me and memorize every single structure of the entire thing. Which, who do you think forced me to do that? Professor Milski. Fucking love that guy. All right, next. So if we had the, oh fuck, I could have just erased the R groups, dude. God damn it. Whatever. Huh? Nah. I already started, you know. It's already started, so no point turning. All right, next is the aromatics. Or just aromatics, right? Actually, they're not all nonpolar. The aromatics. There's 3 of them. And none of them are kinky. Proline's the only kinky one, unfortunately. That's why biochem is so boring. I actually love biochem. I really love biochem. It is. It's very medically relevant as well. This class of amino acids specifically is incredibly medically relevant, and I'll tell you why. So our first little dude is the one that everyone loves to remember, and the one that I always forget how to draw, tryptophan. Yeah, so the way I draw it normally, it's not actually like how you're supposed to draw it, but I just draw it like this because it's easier. Tryptophan. So you got a 5-membered ring with a nitrogen in it connected to a benzene ring off of a carbon. But it doesn't kink because the nitrogen's not involved. Right. All right, guys, how do you, my biochem people who know the joke, how do you pronounce tryptophan properly? Tryptophan. Tryptophan. Because the 1-letter code is W. So this is tryptophan. TRPW. Who stole the T? Well, tyrosine and threonine both stole the T, but threonine got to it first. Tryptophan. Tryptophan metabolism is really... Bitch. Yeah, well, what, you scared of a roach? I'm scared for my shoes, dude. Yeah, that bitch exploded. I don't want blood on my shoes. Yeah, now he's dead. Tryptophan metabolism is really important in the body for the synthesis of 2 very special things. One of which I can remember. I don't remember the other one. One of them is melatonin. Melatonin. Melatonin synthesis and your circadian rhythm is dependent on tryptophan metabolism. You can look up the other one. They are different. We'll get there.
Melatonin what?
Melatonin and something else. Melatonin and serotonin. Oh, and one more big thing. Sorry, 3 things. Melatonin, serotonin, and NAD. NAD. Well, NAD is like, yeah, it's like an oxidative reductase cofactor. We talked about NAD all the time, right? It's used everywhere. Right, serotonin and melatonin come from tryptophan, right? Let's do the other ones. The other 2 are actually cousins. First, we got alanine, and we got phenylalanine. Oh. Oops, foreshadowing. The other one is tyrosine, which is phenylalanine with a OH. So it's a phenol on top of alanine, and this is a phenyl on top of alanine, right? So that is, where's my marker? Phenylalanine. PHE, what's the 1-letter code? Is it P? No, that's proline. It's F, because phenylalanine. Why isn't it H? H is histidine. Why isn't it E? I don't think there is an E. No, glutamic acid. Yes, glutamic acid is E. Very good. You're sharper than I am. And this is tyrosine. Tyry. We talked extensively about tyrosine during one of our lectures. What was it? Tyrosine is a radical scavenger. It can use that OH to bond radicals and disperse the radical throughout the benzene ring. And then later on, when we talk about radical scavenging and the biomechanics and like sort of thermodynamics of biochemistry, we will talk about glutathione, which is kind of the master of radical scavenging. Glutathione. Fly. Like fry, but fly. What's up? What you got? All right, I like that. Fuck you want. That's good. I honestly never really came up with like that many mnemonics for this section because I just like slammed my head against the book and memorized them. I just did it the hard way. Yeah. Let's do everyone's favorite. Let's do the polar side chains, because these ones also, I'm going to ask you guys a question at the end of all of this, and it's going to be a question that comes up on the MCAT literally every single practice exam I took in some shape or form or another. Right? In some shape or form, this question always comes up. So I'm going to save that for the end, so be prepared. All right, let's do the polars. Nah, I already committed. Mama ain't raised no bitch. No, she did not. Oh, God. How many are there? There's 1, 2, 3, 4, 5. 2, 3, 4, 5. First, we have serine. Oh, sorry, the class. This class is the polar amino acids. You guys know why I don't write capital AA? Because that's Alcoholics Anonymous. Not that I told you guys I don't drink. Serine. S-E-R. What's the one letter code? S, very easy. Threonine is a wannabe serine. I never knew why they draw it like this. Every textbook draws it like this. But why wouldn't you just draw serine and then put the methyl group there? Isn't that more like, doesn't it look better?
Yeah.
There's no, it's the same thing. But every textbook you see, and even the MCAT draws it like this. I fucking hate those. No, because it's the same thing. It rotates. This is threonine. And this is the guy who stole everyone's favorite letter. T-H-R-T. Huh?
Feels so right.
Yeah, it does, right? Hey, it feels like it belongs to him. He's important. These two are pretty important. Foreshadowing. So is tyrosine. Do you know what I'm getting at? You know what I'm getting at, right? Okay, good. It's the high energy compound that can do things to those three. Do you get it? Did they teach you that yet? Okay, I don't know if they got up to like thermodynamics and stuff like that. The Orgo people are gonna like that part of the lesson. Oh, fuck. My goddamn arms, dude. All right, next. We've got asparagine and glutamine. Now, unfortunately, I have to teach you the polars before the acidics, but know that these two are derivatives of two of the acidic amino acids, aspartic acid and glutamic acid, right? So asparagine is one carbon and then an amide group, which again resonates, and that's sp2 and blah, 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 whatever. This is asparagine. And these two are also difficult to memorize because they have very strange one-letter codes. This is asparagine, the amide derivative of aspartic acid. It is ASP. What's the one-letter code? N. Asparagine. N. Glutamine is not actually glutamine. It's Q-tamine because the one-letter code is Q. So that's asparagine. Let's do glutamine. Okay, guys, eyes on the board. Asparagine and aspartic acid, whenever you draw them, it's one carbon, functional group. Glutamine is two carbons, functional group. Okay? So look at the board. One carbon will make asparagine, two carbons makes glutamine. Glutamine. GLN Q. Q-tamine. Nothing cute about it. And the last one, and possibly the most important of the entire class, what is it? The most important amino acid you'll probably learn out of all of these, not only for medicine, but for biochem, cysteine. Disulfide bonds, that is correct. Yep. Cysteine. Okay. CYSC. Now, cysteine versus cysteine. CYSTEINE is the amino acid. CYSTINE is two cysteines linked together, which is why you call it cysteine. You don't read it as cysteine, even though that's technically how it's pronounced. It's cysteine, right? That's two cysteines linked together, and we'll talk about how they link together in a bit. You got a mnemonic for this one?
It's a little weird.
What is it?
Slutty quails nest in the.
Okay, hold on. Slutty quails nest in the cold. All right, cool. I like it. Also, a lot of people say, hey, why isn't tyrosine in the polar class? Because the majority of tyrosine is nonpolar, and it's also aromatic, right? You guys like my sweater? I can't wear it because it's hot. It's a Keith Haring. He's my favorite artist. Love Keith Haring. He died too young. Who knows how he died? AIDS. 90s. He was big in the 80s, yeah. He was very good friends with Andy Warhol and Jean-Michel Basquiat. All right, this is good. Slutty quails nest in the cold, right? Okay. What's next? Number 4. We'll do the acidics, and then we'll do the basics. There's only 2 of them, right? And they're the 2. What's next? Number 4. We'll do the acidics, and then we'll do the basics. Okay. Number 4. We'll do the acidics, and then we'll do the basics. There's only 2 of them, right? And they're the 2 that are the original compounds that derive asparagine and glutamine. First one, and the second one. Aspartic acid and glutamic acid. Very good. Okay, so aspartic acid, we said, remember how it was 1 carbon, then amide group? This time it's 1 carbon, and since it's an acid, it's a carboxylate, right? It's going to be deprotonated at physiologic pH. Hold on. That's aspartic acid, and that's glutamic acid. Guys, go back to your notes on asparagine. What did I say the 3-letter code was? ASN, right? Okay, because this is ASP. I'm just making sure that I didn't mess that up. Yeah, so go. I think I wrote P on the board. It's ASN, asparagine, ASN and GLN, because this is ASP. So this is aspartic acid, and also I'm going to write something in brackets. It's also called aspartate, because deprotonated is aspartate, right? This is ASP. What's the 1-letter code? D. And the way you remember this is you remember that aspartic acid is D, and then glutamic acid, which is its brother, is E. D and E, right? This is glutamic acid, which is glutamate. Hold on. I don't want to confuse you. GLUE. So the 4th class are just the brothers, D and E. Right? And you can imagine if you did a carboxylic acid derivative sort of reaction to these, you did an acyl addition, turn that into an NH2, turn that into an NH2, you would get asparagine and glutamine, or cutamine, right? Now, the acidic amino acids are acidic, but, and they're acidic, why? Because they have acidic side chains, and they're deprotonated. But if they're deprotonated, when an enzymatic process occurs, this is important to recognize. When an enzymatic process occurs, they are going to act as bases. They're acidic amino acids, but since they're deprotonated at physiologic pH, they act as bases in enzymatic reactions. Why? Because at physiologic pH, they're no longer the acid form, they are the conjugate base form. So these inside of active sites participate to deprotonate other species. These side chains can pick up protons. And oftentimes on the MCAT, they will say reaction 1 is an enzymatic process that occurs through the deprotonation of blah, 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 blah. And the question will say, which of the following amino acids can partake in reaction 1? And and they're not going to give you the full name. One of the answers is either going to be D or E. And that's going to be the answer. Because if you're deprotonating, ironically, if you're deprotonating, you need the acidic amino acids. So keep in mind that the acidic amino acids are bases in the body, which makes the basic amino acids acids in the body, because they're protonated at physiologic pH. Does that make sense? Yes? Cool. Okay, let's do this. Which are the hardest ones to remember to draw? They're very difficult to draw. Basics. Basic amino acids. There's 3 of them. first one is histidine. And I always forget how to draw histidine. So I'm going to have to keep looking back here. So give me a second. Did not see that. So there's one carbon that goes up, and then it connects into a ring. And this ring goes like this, where there's a double bond, and this connects to an N. And yeah, it's something like this. And I forgot where the second double bond goes. I believe it's next to the nitrogen. Yeah. You go like this, and then you got two H's over here. That's histidine. That group is called an indole group. I-N-D-O-L-E. That ring. It's called an indole ring. This is called what? What did I say? Oh, I did it in the wrong color. Why did no one call me out? Come on, guys. That's pathetic. How did I forget that? All right, well, now I can redeem myself. All right, so we got a double bond and then an N. No, other way around. Double bond and N here, double bond up to the nitrogen and down. This is called the indole group. Right? And this is called histidine. H-I-S, one letter code H, histidine. His. Very important to the biochemistry of hemoglobin, histidine. Very important.
I remember something with DNA, like the orbs that you don't talk about or no?
Histones. Histones.
Yeah.
Ironically, histones don't have histidine in them.
Yeah.
It's lysine and arginine.
Okay.
And I fucked that up in the first lecture that I ever gave you guys. I told you that histones have histidine in them. And now I'm never going to forget it because I fucked it up when I told you guys. It's lysine and arginine, which are the next two. Lysine, okay. Lysine is 4 and arginine is 3. What do I mean by that? Lysine has 1, 2, 3, 4 carbons and then its group. That's lysine. Fuck, wrong color. One, two, three, 4, and then its group. And arginine has 1, 2, 3, and then its group, which is, like I said last time, the guanidinium group, which is very important in the urea cycle. It's interesting. This is lysine, L-Y-S-K, because leucine took L. I don't know why K. Well, L is taken, Y is taken, S is taken, I is taken, N is taken, E is taken. So, K. There you go. And this is arginine, A-R-G, and it's a pirate's favorite amino acid because R. There you go, arginine. Yay, you did it! Woo!
That's common K. Actually, this has have a lone pair. Yeah.
The base amino acids act as what in the body? Acids. Is that a Muji notebook? I have like fucking 20 of them.
Yeah.
Acids act as what in the body? Acids. Is that a Muji notebook? I have like fucking 20 of those, dude. I have so many. You are stealing every ounce of my personality.
No, I just streaming, so do it.
Yeah, sure. Are you looking at me?
No.
There you go. But those are great notebooks. You can buy them like 5 of them for like $250. It's fantastic. Those are my review notebooks. Whenever like I'm reviewing for finals, I'll just fill those notebooks and then toss it away, and then fill and toss it away. Huh? I'm never gonna look at it again. I don't take notes to reread them. I take notes to take them. Okay. Because note taking is linked to memory. So these act as acids inside the body because those protons are able to be donated. So whenever you have a reaction, an enzymatic process that requires donation or protonation inside of the active site, it's more than likely that one of these is lurking inside that active site, sniffing around, waiting for something to protonate. All right, so let's talk about some of the special interactions that occur within amino acids. We're going to get a jump on the future chapters. I don't know if it's specifically talked about within this chapter, but the first one we're going to talk about is likely the one you get asked about the most, and it's about cysteine. So let's talk about cysteine. Cysteine looks like this. And if it encounters another cysteine molecule, what can happen is that an oxidant can come to these two and oxidize them into this weird looking thing. And like we said before, this is cysteine.
Yeah.
Cysteine. And you'll realize a lot of the times when things get oxidized, those hydrogens get taken, because the hydrogens get taken along with the electrons, right? Because oxidation is just stealing the electrons. So when you steal the electrons, you steal the hydrogens as well, right? That's cysteine, right? And that is called it's a special name for this thing. This is called a disulfide bond. And it's a relatively strong bond between two sulfur atoms, right? Also known as a disulfide bridge, right? And you can imagine that if we had a chain of amino acids very long over here, and then a chain of amino acids long over here, and imagine they're both part of the same chain. So look at me, everyone look at me. A chain of amino acids here, and a chain of amino acids here. And you see how they're part of the same chain? A chain of amino acids very long over here. And imagine they're both part of the same chain. So look at me, everyone look at me. Look at my two arms, right? So I have a chain of amino acids here and a chain of amino acids here. And you see how they're part of the same chain, they're part of the same body? Imagine at both of my elbows, like on the inside part of my elbows, this is also called the cubital fossa, that's the proper name for this part of your body, right? So if on both those sides, I have a sulfur, SH group right here, SH group right here, they get oxidized. See how they can bond across here and bond my arms together? Imagine a line connecting the two of them. Do you see how that forms a loop? It'll form a circle. Disulfide bonds form loops inside of proteins. They form loops, closed circles. What's one protein that is chock full of disulfide bonds? No. Well, I don't know, but there's a specific one I'm looking for. Keratin. Keratin. right? And Professor McEntee taught me this in ninth grade, in freshman year biology, right? Oh my God, I'm so old. So she taught me this in freshman year biology, that when people get perms, what's happening is that they chemically break all these bonds, set your hair into curls, and then the bonds reform, these disulfide bonds reform in the curled structure, and that's what gives you those permanent curls, right? Does that make sense? Because it reforms like that. And these are very strong bonds. Also, when you straighten your hair, right, you're basically using the heat to break those bonds temporarily, and they reform in their original structure. And over time, they just start to reform the way they were before. I made a whole TikTok about that. I got like 700,000 views, right? Everyone in the comments is just like, bro, just wanted to show off his hair because I had like really long hair back then. I had hair down like my eyes at that point. I was like fucking shoving it out of my face the whole time in the video. All right, so that's cysteine, right? Cysteine, okay, cysteine, one more thing. When we talk about glutathione later, it's gonna be very, very late in biochem. Cysteine is the part of glutathione that participates in the radical scavenging. So what happens is that the glutathione molecule has a cysteine in it, and another glutathione molecule has another cysteine in it. And what happens is that it gets oxidized by the radical, and you get a cysteine radical on one side, and then a cysteine radical on the other side. And those two glutathione molecules will pair and form the disulfide bond. And then NADPH will come and reduce them back into glutathione, right? We'll talk all about that later. And remember, I still have to teach you guys the difference between NAD and NADP, right? Because there is a difference. But if one of you guys wants to go home and look it up and teach me the difference between NAD and NADP plus, a couple brownie points. Huh? Well, yeah, but what about it, right? Because it's a hard answer to find online. All right. One more thing. I need to talk to you guys. Who here went to specialized high schools? Which one did you go to? SI Tech? All right, I need to talk to you guys about STI. But not Stuyvesant, we have to talk about STI. S-T-Y. All right, let's jog your memory. What do S, T, and Y stand for? It's serine, threonine, and tyrosine. So let's draw them out, right? Do you guys see how the lectures in biochem will take a lot longer than orgo and gen chem? This is still chapter 1, and we're only halfway done. It takes a lot of time. My voice is getting like broken. Huh? Yeah. You require, like, the foundation is very, very dense. All right. So who can tell me the commonality between these three amino acids? OH, right? It's very obvious. You see this OH group right here, this OH group right here, and this OH group right here. I need all of you to listen very carefully, because this will undoubtedly get you a point somewhere on the MCAT. These three amino acids are the amino acids that can be phosphorylated. And be phosphorylated. These amino acids are the amino acids that can be phosphorylated. These three amino acids can be phosphorylated. Why? Why are these the three amino acids that can be phosphorylated? It binds to the OH group, correct. Also, I don't have Jolly Ranchers with me today. I'm sorry. I owe you like 7 at this point. Okay. So the OH group seems to be necessary for phosphorylation. Let's talk about why, right? You guys want to talk about why? Because this will allow us to skip a very large discussion in chapter 12 of Biochem if we do it now, okay? I'm gonna erase this. Okay. And once again, we've drawn this like 4 or 5 times at this point. So we have adenosine, and then we have attachments to our phosphates, and this is gonna be ATP, right? You guys do not need to write this down. Just look at the board, please. Okay. This is ATP, adenosine and those 3 phosphates, ATP, right? In order for a phosphorylation to take place, we need to take the alpha, beta, gamma phosphate and remove it from the molecule, right? By breaking the phosphor and hydride bond. And when we talked about carboxylic acid derivatives, I told you that for any carboxylic acid derivative with this general structure, the active site of the molecule is the carbonyl position, right? So we understand that in order to break the phosphor and hydride bond and trade off the phosphate, we probably need to attack here or here, right? Now it's quite difficult for a nucleophile to get in with all that electron and negative charge shit going around over there, right? But enzymes make it possible. Enzymes create favorable conditions for the reaction to happen. Because what are enzymes? Enzymes are just catalysts, right? And what do catalysts do again? Catalysts take activation energy and lower it, right? So if we make the reaction easier to take place, if we allow for proper conditions to occur, just like solvating a carbocation inside of alcohol or water to stabilize the charges, or a nucleophilic reaction to take place in a polar non-protic, aprotic solvent, right? That would lower the activation energy in the same sense that catalysts do. So solvent, mind you, solvents aren't catalysts. I'm just talking about making favorable reaction conditions. So the enzyme will somehow make favorable reaction conditions for this to happen. Now imagine that you want to attack that with something, right? You want to attack it with something. The most favorable thing to attack it with would obviously be a nucleophile, something with an electron density, and enough electron density to get in. But also so much electron density that it gets repelled. And it just so happens that oxygen is your best bet. So oxygen can sneak into here, kick this up, and make the O minus. These electrons will fall back down and kick off that way, right? That's the whole TCAI move. 1, 2, 3, 4, right? Kick up. So oxygen can sneak into here, thing with an electron density, and enough electron density to get in. But also not so much electron density that it gets repelled. And it just so happens that oxygen is your best bet. So oxygen can sneak into here, kick this up, and make the O minus. These electrons will fall back down and kick off that way, right? That's the whole TCAI move. 1, 2, 3, 4, right? Kick up and kick away. And that's going to attach the phosphate to the oxygen. Do you guys want to see that full? I know I've never drawn the full thing out. Do you guys want to see what the full thing looks like? Would that help you guys, the orgo people? The full reaction, like instead of the 4 arrows. Because that's not the full reaction. Okay, let's do that. Because we're probably going to be here for 3 hours anyways, just discussing this first chapter, so we might as well. Yeah. Someone please make sure that my phone's still recording. Good. Okay. So in orgo, we got very used to seeing this happen, right? And the intermediate looked like this, right? And then this came down and kicked off X, and that made, right? Okay. And that's going to make what? Almost broke chemistry. Right? And now you can see that the phosphate still accommodates 5 bonds, just in a different manner. In a different manner, right? Okay? And now when these electrons from the oxygen that we kicked up to, when they come back down, we can either kick off what was attacked and go back, or we can move forward by kicking away from the rest of the molecule, right? I should add these in. We can kick away from the rest of the molecule, right? So we kick away, right? And also, I'm going to transfer that H plus over there while we're doing this, right? Or, sorry. So now we have adenosine, O, P, double bond O, 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 P, double bond O, O, H, O. And R, O, P, O, O, O. So you guys see how the oxygen gets phosphorylated. It attacks, kicks up, kicks off the rest of the ADP, because now this is ADP, and phosphorylates. So oxygen is required for phosphorylation, which is why serine, threonine, and tyrosine are your 3 amino acids that can be phosphorylated. Because this R is basically just the rest of the acid, aside from the OH group. Does that make sense? Very good. Good? Yes, this helped to kind of see how that happens. And remember, that hydrolysis of the bond releases energy, and the separation of negative charges. You have a bunch of negative charges here. The negative charges move away from the rest of the negative charges, and that releases energy as well. Because it takes energy to keep these negative charges built up together. It releases energy, right? And how much energy? Negative 31 kilojoules per mole of ATP hydrolyzed. Thank you. Smart man. We good? All right. So I'm going to keep that on the board for one more second because I want to show you one more thing. Who knows the first step of glycolysis? Who knows the first step of glycolysis? I do. If I didn't, I'd probably quit. Phosphorylation of glucose, right? So here's glucose. Right? This is beta D glucose. And this is also glucose. How did I tell you to write glucose? Flip off the board. Your fingertips are the OHs. Flip off the board with your right hand. Flip off the board with your right hand. Your fingertips are the OHs. There's 4 of them, and your thumb is the aldehyde group. Fuck, I got a cramp. Huh? Right? Potassium. There we go. Okay. H, 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 H. And it mutorotates. That's called mutorotation, the opening and closing of the ring, right? The beta-D glucose, right? The first step of glycolysis is to take glucose and take an enzyme hexokinase, ATP, ADP, glucose, and let's draw it. O, P, O, O, O. Glucose 6-phosphate. G6P. And you see, oh, big fuck up right there. Huge fuck up. There you go. faster. Stupid glucose. That's glucose 6-phosphate, right? Why is it 6? Because this is the 1 carbon. It's 1, 2, 3, 4, 5, 6. Glucose 6-phosphate, right? So you see that the OH group is what got phosphorylated, right? And this enzyme hexokinase is the one that lowers the activation energy of this reaction. Because if you were to take glucose, and I think I've explained this to you guys before, but I'm going to reiterate because, in all honesty, you guys probably forgot because it's not really taught, right? And that's okay. That's why I'm repeating it so you guys will remember for next time. And if you forget next time, we'll talk about it again and again and again and again until you remember, right? Okay. If you took glucose and it just tried to raw dog the ATP, just nothing, anything, right? It takes this nucleophilic oxygen and tries to shove it in here. It's just going to get repelled immediately. It's going to get repelled immediately, right? All those negative charges, all those electrons, everything is going to anything, right? It takes this nucleophilic oxygen and tries to shove it in here. It's just going to get repelled immediately. It's going to get repelled immediately, right? All those negative charges, all those electrons, everything is going to repel the shit out of that OH, right? What hexokinase does is it cradles the ATP. It holds it like a little baby, right? So let's draw an enzyme around the ATP. And this is the active site of the enzyme. It cradles the ATP. So this is hexokinase, and it's cradling the ATP. And right at the position, this is how fantastic biochemistry is, how beautiful it is. Right at the gamma phosphate position, where it orients the phosphate group this way, it plops a magnesium cofactor right there. It plops a magnesium ion right there. And you know what happens. Now you remember what happens. The magnesium, what does it do? Positives attract negatives. So the magnesium pulls up on all of this negative charge really strongly. It pulls it all up. So instead of looking like this, it looks a little more like this. And it's almost like pulling up the skirt of the phosphate and opening up the anti-bonding orbital for attack by the oxygen. So that magnesium cofactor takes the armor of the phosphate, it takes the electron density and strips it off. And now it's labile for attack by the oxygen. So that's how it lowers the activation energy, because if you were to keep that electron density there, if you kept the armor on the legs of the phosphate, you would never be able to penetrate, and you'd never be able to hit the anti-bonding orbital, right? You'd never be able to get the phosphorylation going. And you'd have to input a lot of energy to overcome that electrostatic repulsion. But you put a favorable process on top, right? The attraction of the negatives by the positives, and you open up the site of attack of the phosphate. Understood? It's a beautiful, beautiful way of examining how reactions work. Good? Okay. Let us take a 5-minute break. And we'll split this up into 2 parts. All right, we're back. Here is...
Okay, so my mom is calling me to come and help her outside. So I'm gonna take a little break and start back this probably later tonight. Probably go for like a longer stream. Okay. Thanks if you were here and joined in. Really appreciate you guys. Like, aww. Okay. Bye. TTYL.